remember to record. Okay, good. So today I want to continue our discussion on standard deviation. So yesterday we spent a fair amount of time talking about calculating standard deviation, and you will have some chances to do that in your homework. But as I said yesterday, for the most part, we'll be spending our time using it and interpreting it. When we need to find it, we'll use Excel or the calculators or some other technology to do most of those mechanics for us. So I do want to remind you a bit, though, what it represented. So let's say we have a data set here. And I have a nice specific example of a data set I want to use later, but this one we're going to keep fairly abstract. So it's just some, random set of data. And I don't even want to look at what the individual data is. I just want to look at what the mean is. So I'm going to say our mean is equal to something nice. How about 50? So let's say, it's just to have something. Let's say it's how much money we make on jobs. So we do little jobs or odd jobs or whatever, and on average we make $50 on these jobs, whatever they are, however long they take. We make an average of $50. Now, a lot can change depending on whether that's everywhere from $47 to $53, or if that's everywhere from nothing up to $100. So that range of data matters quite a bit. So that's why we want that sense of spread here. So let's say the standard deviation that we find as we've been collecting data on how much money we make over the years. Let's say that standard deviation is, how about $7? So in comparison to $50, $7 is not that high. So that gives us a sense that it's a fairly tightly grouped together set of data. If our standard deviation was, say, only $2, okay, then we're really tightly bound together with our data, and we'll look at what I mean by that. If our standard deviation was more like $10, well, then we're making everything from $20 up to $80. It's a bigger range. So whether or not your data is tightly clustered or not is kind of a combination of not just how big your standard deviation is, but how big your standard deviation is in comparison to your overall data or your mean. For example, if we, instead of an average of $50 jobs, if our average was, say, $2,000, with an average of $2,000 with a standard deviation of 7, that is extremely tight, because 7 is so small in comparison to a 2,000. In comparison to 50, 7's fairly small, but it's not nothing. If our average was, say, 10, a spread of plus or minus $7 on $10 is a big spread. So you can't just look at the standard deviation and say, hey, is this data spread out or not? You really do have to compare them. So what does the standard deviation tell us? Well, we talked yesterday about being within one standard deviation is our typical data. So for this example, most of the data, the typical data, and we'll talk about how many we mean by most or how many we mean by typical. but in a little bit. But so our typical data would be one standard deviation above and below. So for this particular example, our typical data would land between $43 and $57. So our typical values would land in that range. Within 2 standard deviations is our usual data. Now, people sometimes ask, well, what's the difference between being typical and being usual? And the answer is 1 standard deviation is the difference between being typical and being usual. Now, again, in casual, as we talked about yesterday, in casual conversation, we often use some of these words more interchangeably. We use them more casually. When we start talking about statistics, we start using these languages much more specifically. So when you see that word usual in any assignment, in any homework problem, in any test question, that word usual should immediately connect to 2 standard deviations. For this particular data, our usual range is going to be between 36, if we subtract another 7, and 64. The last one we talked about last time, within 3 standard deviations, is going to be almost all of the data. Now, oftentimes it will be all of the data, but sometimes there's 1 or 2 data points that sneak out of this, and that's okay. So for example, we might have never had a job that we made less than $29. We might have never had a job that we made more than $71. But at the same time, we could have had that one job, say, that we got $80 for because it was a particularly big job or a particularly good job or whatever. But still, almost all of the data should fit within that 3 standard deviations. So for example, if somebody said, on a particular day, on this day, we made some amount of money. So how much do you want to make that day? On this particular day, we made, say $48. So is $48 a fairly typical amount to make? Is it unusual? Is it outside of the almost all range? Well, 48 is solidly between the 43 and the 57. So $48 is a fairly typical day. It's really close to our 50. It's not more than $7 off. It's very typical. We might be asked things like, is a day where we make let's say, how about $34? I'm going to say only $34 unusual. Alan, you say yes, it's unusual. Yeah, it's outside of 2 standard deviations. It's not much less than this 36. So it's not much less than 14 under R50, but it is outside of that range, so it is unusual. Is it going to happen sometimes? Oh, absolutely. We expect it to happen every once in a while. It's not outside our almost everything. but it is unusual. Now, it might at some point be nice for us to kind of take these ideas of unusual, typical, almost all, and make them a little more solidly numeric. But to do that, we need to make a couple of assumptions. Because what exactly usual, how much data exactly is within 2 standard deviations or 3 or 1 depends on how the data is distributed. So if we make the assumption that our data is distributed in a nice, symmetric, bell-shaped curve, you'll see this curve a lot in this class. This kind of curve, this shape, is often referred to just as bell-shaped, but it is also what we refer to as normal. Norm data, or normally distributed. Notice I avoided using the word normal over here. That's why I avoided using it, because normal is what we say for data that is distributed, nicely, normally. It should be symmetric about some location. And it's kind of what we expect, a lot of data to be. There's a lot of values clustered close to that middle, and less people weigh on one end, less people weigh on another. So if you were studying things like, I don't know, heights of men in the United States, most men are somewhere near the average in height. The shorter you look, the less people there are at that height. The taller you look, the less people there are at that height. So, male heights would be a nice bell-shaped curve. By the way, I specify male heights because if you look at people heights, like human heights, your curve actually looks like that. It's got a bump where the average female height is, and it's got a bump where the average male height is. So it wouldn't be normally distributed. It's got 2 high points, so it has 2 modes. So we'd actually call it bimodal data. So if you're wondering why I specified male heights, that's why. You'll have a little bit of examples of bimodal data in your reading. But because of the symmetry, our average is going to be at or near that peak along with the mean. So as we talked about yesterday, that 1 standard deviation from the mean, so in this case from our 50, assuming our pay is normally distributed in this bell-shaped curve, the amount of data in this section, the amount of days in which we will make pay in that section, is fairly fixed at almost around 68%. So if our data is normally distributed, about 68% of our values will be in that typical range within 1 standard deviation of the mean. So almost, but not quite 70%. So that's the majority of our data. If we go out further, if we go out to 2 standard deviations, 2 standard deviations is supposed to be usual, so it's unusual to be outside of 2 standard deviations. So that's our 64 and our 36. So in this range, again, including our typical data is still usual. It's just also typical. That got squirrely, sorry. So in between two standard deviations, we've got 95% of the data. And that's it's really close to 95%. It's a little tiny bit off. We'll talk about that later, but it's a good approximation, about 95%. And that's a pretty standard threshold for when we call something unusual. Something unusual should fall in the outside 5%. So when you hear someone in business or sociology or science especially talking about whether something was unusual or not, they're usually talking about it being that outside 5%, 2.5% down here, 2.5% up here. Lastly, that 3 standard deviations, the 29 up to the 71. I said that should contain almost all of our data. Well, how close to all do we mean when we say almost all? Technically, and we'll get more flexible with this later, but technically we're talking about 99.7% of your data should land within 3 standard deviations of your mean if your data is normally distributed. So if we knew that the average height of, let's say the average height of the kids on our baseball team, so the average height of these baseball players, average height of the players was, say, 48 inches. That's 4 feet. They're little kids. The average height of the kids on our little baseball team is 48 inches. And the standard deviation was, say, kids are really spread out. So let's say it's, let's say it's a whole 10 inches. Do I want 10 inches? No, I don't want 10 inches. It's way too big. Sorry. Way too big. Let's say the standard deviation is 4 inches. Assuming this data is normally distributed, then we could say 95% of our players are between 1 height and another height. 95% should be our usual data. 95% is 2 standard deviations above and below our mean. So we're going to be 2 4s, or 8 units, above and below this 48. So 95% of our players are going to be between 40 inches and 52 inches. 52. No. I can't add 8. So 48 plus 4 would be 52, but I got to add it twice. Plus 4 again would be 56 inches. So that's a pretty big range of heights. Of course, kids often vary quite a bit in height. But if you were trying to make sure you got, enough uniforms or the right size of uniforms to fit all the kids, you probably use this unusual data or this usual range. If you go between 40 inches and 56 inches, you're going to cover 95% of your players. Yeah, there'll be some of your players that you're not going to be able to fit right. Always being one of those really tall people that nothing ever fit right on. It does happen, and it can be frustrating. But your other option would be to make sure you go, say, 3 standard deviations out almost all would be between what would be another 4 in both directions, be between 36 inches, and another 4 would be 60 inches. So that's from 3 feet to 5 feet. That's a big range. So oftentimes you'll see companies, when they design things, they won't try to get everybody. They won't try to get almost all. They'll try to get about 95%. That way they can, sell their products to 95% of the population. They'll miss 5% of the population, but it stops them from having to build such a big range into their things. Depending on what you're trying to sell and how expensive it is, but for example, if you're trying to buy a fancy sports car, and you want to make sure, am I too tall or too short for this sports car? Often the more expensive the item is, the tighter they get, because again, they don't want to design in a wide range, but they want to make sure they fit enough of their population that they have a market. Sometimes they'll go down to this 70%. So they'll go down to 1 standard deviation above and below. They know that'll hit about 70% of the people out there, and they'll focus on that market. This, by the way, is called, does have a name, these percentages are referred to as the empirical rule. The empirical rule says if our data is normally distributed, we expect 68% to be within 1 standard deviation of the mean, 95% to be within 2 standard deviations of the mean, and almost all of our data, 99.7%, within 3 standard deviations. We will refer to this rule a lot. Questions about that? If you're curious about, well, what if, how much is only half a standard deviation above and below? Well, what if we're, 1 1/3 standard deviations above and below? Could we figure out those percentages? Absolutely. And we will. We'll call it Chapter 7. So we've got some tools we want to build up before we do that. But we will get a lot more specific in here. We'll be able to find, really, to a high level of accuracy, almost any amount you want in here. So if we wanted to know, for example, how many days or what percentage of our days do we make between, say, $48 and $51, if we wanted to know what the percentage in that particular range was, we could find that. But we need some tools first. This empirical rule is a nice, quick set of rules, and it's just, well, it uses the same tools that we will use in Chapter 7, by the way. But it's just, hey, for 1 standard deviation above and below, 2 standard deviations, and 3 standard deviations, it's nice to just know those and have those at hand when we need them. We'll get more specific later when we can. Okay, where do I want to go from there? Ooh, let's do that. So, given a data set, again, I have a specific one I want to use in a little bit, but I want to stay kind of abstract here for a bit. So given a data set with a mean of, let's stay super nice, mean of 100 and standard deviation of, let's go with 20. Oops, it's not a question yet. What proportion of values are between, now let me think here for a minute, between, let's do that, between 60 and 120. So we've looked at the tools necessary to determine that, but there is a little bit of a hiccup in it. So take a minute. I do recommend when you have problems like this, draw this distribution out in one way or another. You know, give yourself an axis, label it with your first, second, and third standard deviations. That visual reference will be surprisingly helpful. So draw that out a bit and just try to decide how you would approach this question. This is a fairly common type of question. We're doing it right away, but so it might be a little bit sticky right now. But just how would you approach it? Oops. Can give you a minute to play with that. So let's play with this a little bit. So we know the center of our distribution is at that 100. So I'm going to put it in fairly light here. But so we've got a distribution above this that is symmetric. Our standard deviation is 20. So that 120 is one standard deviation up. 80 would be one standard deviation down. That 60 is two standard deviations down. So we know between the 80 and 20, we know what percentage or proportion of our data lives in that range. So that blue range is going to be 68%, or because we're asked as a, I did say proportion up here, the proportion is 0.68. So that's the blue part. But we also need this orange part. So we got to figure out how much is in that orange part. So I'm going to go off here. Ooh, draw a terrible diagram. I want to redraw that diagram. So I want to talk, can we figure out what the little sections, how much are in each little section? Not sure how much better that was, but that's okay. So if that's our mean, if one standard deviation out contains 68%, if I think of this as two separate boxes, how much are in each of these separate boxes? If 68% is supposed to fill it, this had better be 34%. And that had better be about 34%. Is that fair? Okay, if we go out two standard deviations is supposed to be a total of 95%. But if we want to know how much is out here, how much is in that atypical but still usual range, we'd have to subtract off that internal 68%. And what is 95 minus 68? If we just want that part, is 27. That seems reasonable. So all of that green is 27%. If we want to know what is the size of each one of those green pieces, it's going to be half of that. So the 27% divided by 2 is 13.5%. So each of those pieces are 13.5% and 13.5%. We could go even further than that if we wanted to, and we might as well, we're right here. If the two standard deviations have 95%, that means outside of that should be the other 5%, half above and half below. So 2.5% and 2.5% outside of that. Now, if we want to go to the third standard deviation instead, we'd have to take off, what, 0.3% from that total? It's still about 2.5. So roughly speaking, the tails outside of two standard deviations are each 2.5%. Our sections, each section between 1 and 2 is 13.5%. And each section between the mean and 1 is 34%. This isn't what we call our empirical rule, but this is a consequence of our empirical rule. Our empirical rule is just the 68, 95, and 99.7, or almost 100. But as a consequence of that, we can break it up and look at these pieces. And it's going to be handy often for us to do that. So what that means, coming back to our problem, is that this orange section here is 13.5%, or as a proportion, as a proportion, 0.135. So if we want that whole thing all put together, we want the 0.68 plus the 0.135, which is going to be, what, 518? So 0.815. So what proportion of the values are between 60 and 120? A proportion of 0.815, or if you prefer, 81.5%. Again, if you're asked proportion, we should really answer in proportion form, but if it helps you think about it in percentage, because we're more accustomed to that, that's fine too. What was that, Tessa?
Sorry, I accidentally unmuted myself.
Oh, no problem. So questions about that? Good, Ivan. Hopefully you can see that there's actually a fair amount of types of questions and types of information that we can get out of this kind of information. It's not skewed because it's symmetric. Our empirical rule, the first part of our empirical rule says if your data is normally distributed. As soon as your data becomes skewed, these percentages start to change. And how much they change depends on how much skew there is. Oftentimes, if your data is just a little bit skewed, you'll kind of go, as really common, you kind of go, okay, it's close enough to normal that we'll use these rules, but just know that they're going to be a little bit off. If your data is fairly skewed or highly skewed, you have to approach your data from a different perspective. So a lot of the data that we will use in here will be normally distributed, will be fairly nice and even. Or if it's not, there are some tools that we will learn that make it normal, that force it to act like a normal distribution. But the empirical rule, as it's stated here, is for nice symmetric data. I'm not sure, Alan, if I understand that question. Would 90 be the mode? Oh, I see what you mean. No, because the data is nice and symmetric for this 100, that 100 is the peak. So that 100 is the mode. It's also our data's median. In normally distributed data, in any symmetric data, but normally distributed data, your mean, your median, and your mode are essentially on top of each other. Now, it might look like the peak is a little off that 100. If so, that's just my diagram. Cool. Okay, so as I said, I did have a particular data set I wanted to look at a little bit today. And to look at that, I want to jump over to Excel. I'm going to bring that over here to unpause it. Okay. So bring us over to Excel here. Moved all my stuff around. Okay. So what I've got here is a list of birth weights for newborns listed in pounds. So 9.5 pounds, 6.6 pounds, 5.3 pounds, and so on. And I want to find well, really, I want to find all of the descriptive statistics that we've talked about so far, but I want to talk about particularly our mean, our standard deviation for this data. Now, certainly, if we wanted to find the mean for this data, we could add it all up by hand. It's all written there. You could add it all up, and you could divide by how many there are. But that would be a lot of work, and Excel is supposed to do the work for us. I am going to take a moment and sort this data. On your lab, you guys saw how to sort data. So I was going to go over to our data sort down. Yeah, it's okay. Nah. Why didn't it sort? No, do the current section. Yeah, thank you. Excel is being argumentative. So that's got all of our data nice and sorted in case we need it sorted or want it sorted. So if we wanted to find the mean, again, we could add them all up, and Excel has a tool for adding stuff up. But we actually, Excel also just has a plain straight command for finding the mean. So if we wanted to find the mean of all this data, we can literally type in equals. I want this cell to equal our average. So I'm going to have to type that equals first. That gives us access to the commands. And it would be nice to be able to type in mean, but Excel wasn't written by statisticians, so they didn't use the word mean for the mean. They used the word average. And then I'm going to start a parenthesis. So unfortunately, we can't use the nice word mean. We got to use the word average. But we're used to thinking of average as the mean anyway, so that's not too terrible. Now, then it's asking for the numbers, number 1, number 2, number 3. So again, we could type in all of those numbers, but that would be a lot of work. We don't want to do that. So instead of typing in all those numbers, we're just going to highlight them. Grab, highlight down to all the numbers, hit enter, boom. I'll scroll back up. That's our mean. I'm going to label it here, mean. So that's nice. Nice and quick. You could, of course, also type this data into your calculator and use its one variable statistics tool to find the mean. But typing the stuff into your calculator, I find to be a bit of a pain. But if you like interfacing with the calculator, great, do it that way. If we wanted to find standard deviation, we could take each of these numbers, subtract them to find the deviation, square each of those values, add the squares up, divide by the adjusted average, and take the square root, like we did yesterday. And frankly, Excel makes that easier because it does the main calculations by itself. But wouldn't it be nice if there was just one command we could give it? No one's nodding emphatically. You know there's just one command we can give it, right? So there is. If we want Excel to do it for us, just equals. Again, anytime we want Excel to calculate something, we got to use that equals. So equals ST. Notice as soon as I start typing, it starts to guess what I want. And standardize, I don't want standardize. STDev, that is our standard deviation. So you could highlight those or click those. I'm going to type the rest of it. But notice there are two of them. There's standarddev.p and stdev.s. The .p is for finding the standard deviation of a population. If you have all of the data for a population, we'd use that one. As you might remember from yesterday, I said when you're doing a population, you don't find the adjusted average. You don't use that n-1, you just use the n. So that's the difference between these two tools. So be careful about that. That also does happen on your calculator. It gives you both of them. So we want the standard deviation for a sample because this is not every child that has ever been born. So we're going to use the stdev.s. stdev.s. Parenthesis to start our data set. And again, we're not going to type them in. We're just going to highlight them. Enter, scroll back up, standard deviation. To as many decimals as we need. You know, it's going to give us what, 4 or 5? Oh, 12? So a fair amount of decimals. The smaller you make this, you'll see less decimals. You can also control the decimals up at the home screen. This little number box will allow you to, oops, other way, allow you to move how many decimals it shows up or down. So I'm going to stick with it just showing those two. So for our birth weights, we have a mean and we have a standard deviation. While we're doing this, we might as well find a median. And again, we could find the median, especially since we already have them in order. We could find out how many data points that is. That's 26 data points. Should say it down in the corner, count 26 when they're all highlighted. So 26, half of 26 is 13. So it's going to be the 13th and the 14th. So we could count down to the 13th and the 14th and average those together. But again, wouldn't it be nice if we could just type in median? Yep, it would be absolutely nice if we could just type in median. And then highlight our data. So once you get used to manipulating Excel a bit, finding these values actually goes pretty quick. There is a way to make it give it to us all at once, but frankly, if you just want 2 or 3 of them, just typing those out is easier, I think. You could also use the calculator. It has a tool for finding all of these as well. If you need help with that, let me know. So there's lots of ways that we can get this data. But right away, we could jump to trying to ask questions about these things. I'm going to move that over here. Sorry, give me a second. Make it easier for me to see this. That's better. So if I wanted to have a question here, like, you know, what birth weights would be considered unusual? We should be able to use these descriptive statistics to find what our range for unusual would be. So take a moment considering what we've done so far and determine what would be unconsidered, what values would be considered the high and low for our usual set. I think I'm going to wait to get an answer from at least 2 of you. So 76 plus 1.6, 9.6 unusual. So Alan, you took the mean and added and subtracted 1 standard deviation. For unusual, what do we use? 2 standard deviations, exactly. So 1.6 plus and minus, we actually want twice that, plus or minus. So the nice thing, again, we can actually have Excel do it for us. Nice thing about Excel, you can be really lazy. So if I want to add and subtract 2 of these, I'm just going to go to a cell, hit equals, because I want it to do something for me. I want to take this mean. Notice I'm not going to type the 7.6. I want it to take the value in this cell. So I want it to equal this mean. Notice it says D3. It's calling the value in the cell D3. And add 2 times the value in this cell. So that's my upper bound. It's especially nice because then if this data changes somehow, or we add more data, let's say this, we find out, nope, that was, 10.2. Notice that changed my standard deviation and my mean. Because the mean and standard deviation are calculated based on what this list is, if this list changes, those values change. Now, when those values change, because this called those values, it changes as well. This is one of the handiest things about Excel, is that if you give it a command in terms of references, when you change other data, all those references automatically update. So getting in that habit of calling information as opposed to typing it is really, really helpful. So if that's the upper bound, I want the lower bound, so I want to subtract. So again, equals. If you don't hit equals, like notice sometimes people will forget to hit equals. I do it all the time. You'll go to call that cell and it will move instead. The equals locks it in and says, hey, I want to call this cell my mean, and I want to subtract 2 of those. Equals. And that gives us our range. So birth weight will usually be between, I'm going to say 4.4 pounds and 10.8. Because of course we always answer word problems in sentences, so. And rounded to 1 decimal because that's our standard unless otherwise asked. The homework in the book often likes you to round it to different places. Whatever they tell you to round it to, round it to. And you might say, well, why are these so decimal-y if this is just 1.6? Remember, it's calling this cell, so it's calling all of that accuracy. It's calling all of that when it does its calculations. So even though we rounded it for just looking at it and being able to talk about it, again, one of the good things about using this program is that because we called them, we called all of that extra accuracy. So we didn't lose any accuracy. So when we do our final rounding, we don't have any error on top of error on top of error, making our rounding different. You can do that with the calculators by storing values, but storing values and calling those stored values, but it's more difficult to do on the calculator, but you can still do it. Questions about any of that? Excuse me. So again, I'm not terribly concerned whether or not you guys want to use Excel for what you're doing or the calculator for what you're doing. I am going to kind of be pushing you a little bit toward Excel because that's most of the examples I'm going to use. And a lot of that is because in a lot of ways, it is a stronger tool for it. It does take a little bit more to learn because you guys are used to the graphing calculators and probably not used to Excel as much. But as you go along in your careers, you will more likely be at a computer with a spreadsheet program. That's what Excel is, a spreadsheet program available. and not near a graphing calculator. For example, I'm Andrea. I'm at work there, right? How many graphing calculators are in that building?
Oh man, we're lucky to even find one calculator around here
Yeah.
sometimes.
How many computers are in that building?
Oh man, I think we have about 20.
So there are 20 options to use Excel, and you'll be lucky if you can find a graphing calculator.
Right, correct.
So being able to use these tools on Excel is going to be handy. So
Right.
try to push yourself to learn, well, both of them preferably. But if you're new to Excel and a little nervous about Excel, hopefully you'll jump in with both feet and try to get more comfortable with it. And not just her, everybody. Okay, so that should give you what you need to complete 3.2. We'll do 3.3 and 3.4 Monday, I guess, because it's Thursday. I do want to leave you there. I don't want to start packing 3 on top of this. This is surprisingly a large amount of information. You've got all the pieces that you need, but sometimes, like that question where we broke it up into parts, sometimes it does take figuring out how to take what we know to use it to effectively answer the questions. So that just takes practice and playing with. As you play with those and practice those, if you run into any questions and need any help with it, send me a message, let me know, post it on the forum, message each other. Hopefully you guys start talking to each other a little bit more, particularly this group, talking to each other or me or anybody. I know, Andrea, you're at work, and Leslie's clearly sitting on a beach somewhere, very happy. That's the only thing I know about Leslie, is she's at the beach. If that's a beach, at a sunset, I have no idea. So hopefully you guys are going to maybe be a little more active in the forums or whatever it takes to be able to, excuse me, whatever it takes to be able to get some of that communication going. But go work on it if you have any. All 6 of you. Was those 6 of you? Oh, I'm only seeing those 3. Oh, those. Oh, all 5 of you. Oh, I missed Ivan. Okay. So anyway, go play with that. If you need anything, let me know. And have a wonderful day. Alan, you doing good?
It varies. Yeah, this early part of this is a lot of information, but it's easier to obtain than the later part, but there's just more of it.
Yeah.
In the earlier part.
Well, and that later part does get a more convoluted, to be sure. But the better this part goes, the more you can get rock solid on the vocabulary and the little details in this stuff, the more grip you'll have for when that other stuff starts to get a little bit weird. So focusing, getting real strong with this stuff pays off a lot.
Yeah. Yeah, it's an adventure.
Yep. If you find something you need, let me know.
I surely will. I still have not heard back about the tutors, but I'm hopeful.
Okay. Keep at that. If it's much longer, let me know and I can see if I can poke them or find you other options or whatever.
That would be great because yeah, it's gonna get tough and I already know I'm gonna need. So all right.
Okay. I'll look into it.
Thank you.
Yep.
Bye.
Bye.